Welcome back to the next video, everybody. Today we're going to be proving lemma 2 of proposition 1 a couple of videos ago. We're going to need Fontaine's categorical equivalence to do this. And you're really going to see like a common theme in modern number theory here, which is turning advanced, kind of deep, complicated mathematics into something simple we can actually do, like linear algebra. So let's recall the lemma. The lemma says if we have a representation rho from GL to GL2 of O mod lambda to the n, L is an odd prime here, and O is like a complete Noetherian local ring, whatever, with maximal ideal lambda, and that's a good representation, then the cardinality of H1F GL add rho is the same as the cardinality of H0 GL add 0 rho times the cardinality of O mod lambda to the n squared. Okay, so we're going to prove this mostly. So let's assume L is an odd prime. We'll let FFO denote the category of good finite O bracket GL modules, and then we'll define a new category MFO, whose objects are O modules D of finite cardinality equipped with a distinguished submodule D0, and O linear maps phi -1 from D to D and phi 0 from D0 to D, such that when you take phi -1 and restrict it down to D0, you get L phi 0, and when you sum the images of the two maps up, you get all of D. We want the morphisms in the category MFO to be O linear maps compatible with this data. Okay. We'll also just make some observations. If D is an MFO, there's a surjection phi -1 direct sum phi 0 from D mod D0 direct sum D0 mod L D0 onto D mod L phi 0 of D0. And if you look at the orders of both sides, you find this is actually an isomorphism. Okay. This, in turn, gives us an isomorphism from D mod D0 plus lambda D direct sum D0 mod lambda D0 with D mod lambda D. And all this is to say that D0 mod lambda D0 has to inject into D mod lambda D. And all that is to say that D0 must be a direct summand of D as an O module. Okay, so that's nice to know. You can also see from this that phi 0 must be injective, for example. And then it's a quick check using this information and a little bit of elbow grease that there's a contravariant functor star from MFO to MFO given by the following. D star is Hom D QL mod ZL. So we have like a duality thing going on here. D star 0, the distinguished submodule, is Hom D mod D0 to QL mod ZL. Phi star -1 of f of z is f of Lx plus y, where z is phi -1x plus phi 0y. And phi star 0 of f of z is f of x mod d0, where z is equivalent to phi -1x mod phi 0 of d0. There's a canonical isomorphism d with d star star, which gives me a natural isomorphism in MFO. And then you can also check that MFO is an abelian category, and so we can do all the usual homological algebra there. And for all kind of the stuff I've said so far, I'll just refer you to Fontaine's paper here. Okay. We are going to black box the following theorem. We will return to this much later. Okay, there is, we'll call it theorem FL1. There's a covariant functor blackboard D from FFO to MFO defining an O additive equivalence of categories. If M is an FFO on this side, then the cardinality of M is the cardinality of D of M, and D of M is D of M0 if and only if M is unramified. Okay. So we're going to use all this stuff this video, but we're going to take this theorem for granted for now, and we'll cover it later. If we apply the first conclusion, by the way, to M mod lambda to the IM for each I, we actually find that M is isomorphic to D of M non-canonically as O modules. So that's nice to know. Okay, back to the proof. First, we need a lemma. So let rho from GL to GL2 of O mod lambda to the n be our good continuous representation. We'll let D sub rho be D of M sub rho, where M sub rho is the representation space. Then D sub rho is isomorphic to O mod lambda to the n squared. That's kind of a definition check on the functor blackboard D. I think we probably need to dig a little bit more into D to see why that's true, but maybe you can think about it. So this is as O modules. And then there's not much room in here, so to speak, if D0 has to be a summand of D, so D0 rho must be O mod lambda to the n. So lemma, the following are isomorphic. 1, the group of extensions of M rho by itself in the category of good finite O mod lambda to the n bracket GL modules. 2, the group of extensions of D rho by itself in the full subcategory of MFO consisting of objects which are O mod lambda to the n modules. And 3, crucially, pairs alpha -1 alpha 0 where alpha negative 1 is an O map from D row to D row, alpha 0 is an O map from D0 row to D row, and L alpha naught equals alpha negative 1 when restricted to D0 row. And then we want to kind of mod out commuting relations here. So we want to mod out pairs of the form A phi rho negative 1 minus phi rho negative 1A, comma A phi rho 0 minus phi rho 0A when restricted to D0, where A here is just an O map from D row to D row, satisfying A D0 row is in D0 row. So we have like an invariant subspace condition here. Okay, let's prove this. That the first two are isomorphic is just theorem FL1, essentially. So we're going to calculate the second extension group and show it's isomorphic to the third. We're going to kind of just sketch this, though. Let D equals D row for simplicity. If I give you an extension 0 to D to E to D to 0, then as O modules, E is isomorphic to D squared. We have projection sections going the other way. That's why via an isomorphism such that E0 is isomorphic to D0 squared, actually. So even on the level of like distinguished submodules, we have an isomorphism like this. Well, another way of saying this, though, is just that E is determined by giving some alpha E negative 1 in Hom DD and alpha E0 in Hom D0D, such that L alpha E0 is alpha E negative 1 when restricted to D0. Wording this purely linear algebraically, though, we can be a little more even concrete and restate this again as saying that the phi minus 1 map on E, written as a matrix, just has the original phi minus 1 map on its diagonal. And this alpha E negative 1 is up top in the top right. And then kind of the same thing holds structurally for the phi 0 map associated to E. It's going to have phi 0 as its diagonal entries and alpha E0 as its upper right entry. And these are both diagonal. Okay. So, I mean, when are two of these extensions, E and E prime, isomorphic? Well, if and only if there's kind of like an ordinary isomorphism from E to E prime respecting the inclusions of D into E and E prime, and the projections, which are section star surjection in the exact sequence from E prime to D, and then also the data of the phi. If you choose module isomorphisms E prime with D squared, this map is, of course, just a 2x2 block matrix. And the first condition on inclusions just tells me that the first block column is I0, the identity in that 0. The second condition on projections just tells me the lower right block is I. And the third condition on respecting the phi sub i's gives me a commuting condition. Okay, so check all this. This is some linear algebra exercise. And then I'm going to be a little bit more explicit about this commuting condition now. If you actually write all this out in terms of matrices, what it says is the following. E is isomorphic to E prime if and only if there exists an endomorphism of D called A, such that AD0 is in D0. We knew that was coming. And then if we take the phi negative 1 map associated with E, which we know is this matrix by the above, and conjugate it by the matrix 1A01, we get the phi negative 1 matrix associated to E prime. And then the same kind of structural thing happens with the phi 0 matrices. If we take the phi 0 matrix associated to E, conjugated by 1A01, the same exact matrix we conjugated by above, we get the phi 0 matrix for E prime. Okay, but then you can just do the math, so to speak. This is equivalent to the fact that if A D0 is in D0, then alpha E negative 1 minus alpha E prime negative 1 is phi negative 1A minus A phi negative 1. And the same thing for with negative 1s replaced by zeros. Alpha E0 minus alpha E prime 0 equals phi naught A minus A phi naught. And then it's a very fast check from here that you actually just get the result for free. The second and third group in the lemma, those are isomorphic. Okay, so here's what we really want to get to. So the first corollary of this discussion is that H1F TL add rho is isomorphic to O mod lambda to the n squared direct sum H0 IL M rho non-canonically. And the proof is as follows. It's kind of just some brute force algebra and linear algebra again. If you choose generators E0, E negative 1 of D such that E naught generates D0, we know we can do this, then relative to this basis, we can write the matrix of phi 0 as, say, xz, and the matrix of phi negative 1 as lxy, lzw. This is just definitions. And if A has matrix A1, A2, 0, A3, you can just directly calculate that A phi negative 1 minus phi negative 1A, comma A phi 0 minus phi 0A restricted to D0 is the following pair of matrices. The first one is LA2Z, A1 minus A3Y plus A2W minus LX, then A3 minus A1 all times LZ, and then negative LZ A2, comma, the next matrix is A2Z, and then A3 minus A1 all times Z. So according to what we've just shown, our group of extensions that we're after is the quotient of the set of pairs of matrices, alpha negative 1, alpha 0, as explained above, quotiented out by the submodule kind of given by what happened up here, which would be the submodule generated by the following pair of pairs of matrices, the first pair of which is LZW minus LX, 0, negative LZ, comma Z0, and the second of which is 0, negative Y, LZ, 0, comma, 0, Z. That's all kind of a quick check for you to do. Since m phi negative 1 plus m phi 0 is D, either Z or W must be a unit in O mod lambda. That's a quick check for you. And so you find that the extension group you want actually is isomorphic to O mod lambda to the n squared direct sum O mod, the ideal generated by Z and lambda to the n. You have to kind of check this in two cases, either Z as a unit or W as a unit. In either case, you can kind of write down an explicit isomorphism between the data up here and what we're after here. And I'll leave that to you. However, on the other hand, H0IL rho corresponds by definition of the D functor essentially to the largest submodule U in D0 such that phi U of U is U. And you can check that that's just all the D's in D0 such that ZD is 0 kind of under this setup up here. And then you can also finally check that this set is just isomorphic to O mod, the ideal generated by Z and lambda to the n, which gives us the corollary. Okay, so I gave you a lot to check there, but it's all kind of like, I don't really want to do it. It's just details and kind of hard work, so to speak. Okay, and then the finale, which is lemma 2. So corollary, let rho from GL to GL2 of O mod lambda to the n be good. Then H1F GL add rho is isomorphic to O mod lambda to the n squared direct sum H0 GL add 0 rho, which will give us the lemma. The proof is not too bad. If rho is not ordinary, first of all, then H0 GL add 0 rho and H0 ILM rho are just trivial by definition of ordinary. So we can go ahead and assume rho is ordinary or the problem isn't interesting. Let's let rho prime be the ordinary representation defined by the representation space M rho prime, which is homomorphisms from M0 rho to M rho, which is of course in add 0 rho. And we'll let M epsilon sub rho prime be add 0 rho's kind of cyclotomic piece given by the definition of ordinary. We have like an identity piece and a cyclotomic piece. This will be the cyclotomic piece. You can check by definitions that H0 GL add 0 rho is the same as H0 GL of M rho prime. Okay, so we can actually kind of restrict down here and lose not very much. This is, of course, in H0 IL M rho prime, which is also H0 IL M rho. Okay, so it's like we can kind of just look at rho prime instead of rho briefly. All right, so we know H0 IL M epsilon rho prime is trivial because this is the cyclotomic piece. Okay, so the restriction homomorphism from H1 GL M epsilon rho prime to H1 IL M epsilon rho prime is trivial. Sorry, is injective, because the H0 part is trivial. Okay. And now you just gotta, I'm not gonna write down any details here. It's not hard though, I promise. If you now take all the information from the proof so far, and you look at the long exact sequences of cohomology, one for inertia, one for the full decomposition group, associated to the short exact sequence 0 to M epsilon rho prime to M rho prime to O mod lambda to the n, which is like that's like our identity piece to 0, and you just perform like a diagram chase on the result, use this injectivity and what we know about various groups already, you will immediately find that H0 GL M rho prime is H0 of IL M rho prime. And then I leave it to you to quickly show that because of this, the corollary follows immediately. Okay, so you see again, like we took some very complicated cohomology and representation theory stuff and finite flat group scheme stuff that's hard to think about. And then Fontaine just gives us a way to think about all this, at least in the way that we need to, kind of purely linear algebraically. And this is a common theme when studying modularity and even like Langland's program at large. And so next time we'll be pushing towards something that I'll call proposition 3, which is the next key step in the proof of R equals T in the general case. But we're going to have 2 setup videos before we get to that. And so I'll see you then, and thanks for watching.